Good afternoon, everyone. Welcome to PLC Blaster, a worm living solely in the PLC. We are currently in South Seas IJ with Mike Brugman. Before we begin, a few brief notes. Be sure to stop by the business hall located in Bayside AB. Also, the Black Hat Arsenal is on in the Palm Foyer on level 3, and the Arsenal reception is at 1700. Also, if you haven't picked up your merchandise today, it is your last chance, so visit the Black Hat Swag and Bookstore, and also visit the Cali Linux Lab and Mandalay Bay A. And thank you all for putting your phones on vibrate. Without further ado, Mike.
Thank you very much. So, my name is Mike, and I'm going to present our research on industrial control systems now. Before I start, I would like to give a short introduction about who we are. I work in a small company called Open Source Security, and we are located in Germany. We are mainly focused on Linux security, but a few years ago we started to pen test embedded devices and related technology, for example RFID systems. In addition, we do pen testing and research on industrial control systems. And that is the reason why I'm here today. We developed a worm which is able to spread over PLCs. Our research was motivated by the Stuxnet worm. Stuxnet was a worm that attacks Siemens PLCs. It uses Windows, bugs in Windows to spread, and that means it requires Windows to spread. Starting from this assumption, we are wondering if it's possible to create a worm that is able to spread without any external hard or software support. And the answer is yes, it is possible. Before I show you how we implemented the worm, I will give you some background information on the PLC we chose for our work. We chose a PLC called S7 1200. It's a Siemens PLC and it's built for a small application. We chose this one because it's cheap. It costs about $150. It has 50 kilobytes of RAM and 1 megabyte of persistent memory. It has built-in Ethernet, and we looked at it in firmware version 3, and we looked at the TIA portal in version 11. The TIA portal is a software that is used to program the PLC. Compared to a usual computer, the system works different. It works in cycles. Each cycle will start with reading the inputs and writing the outputs. After that, the user program is executed. The user program is a piece of software that is written by an engineer and controls the machine, for example, a traffic light or an assembly line or what machine ever. After that, there are other tasks taking place, for example, communication with other PLCs. Each cycle has a time limit. In Siemens PLCs, it's usually 150 milliseconds. If one cycle takes longer than 150 milliseconds, the PLC will stop the execution and switch to an error mode. And the cycle is controlled by the firmware. The program that you can write for the PLCs is structured in so-called program blocks. There are 6 different types of program blocks. The first is called organization block. It's the entry point of the program and can be seen as a main function known from C. There are function blocks. It's basically classes known from object-oriented programming languages. And there are functions. Functions are similar to normal functions known from C. There are system function blocks and system functions. This is a library which is delivered by the vendor. And in the end, we have data blocks. Data blocks are some kind of global memory. You can access it from everywhere in your program and can store any data in it. These program blocks are can be programmed in different programming languages. For example, ladder diagram here, or function block diagram. And these are graphical-based programming languages, and they are used by electricians who are familiar with this kind of diagrams. There are also text-based programming languages, for example, structured text. We chose this one to implement the worm. Yes, if you want to implement a PLC-only worm, you have to do it in the programming language of the PLC. What parts you have to implement? The first part is the target discovery, because the worm has to find its targets by its own. After that, the worm wants to copy itself to the target system, so we need a carrier mechanism. After that, the copy needs to be activated, so the execution of the copy needs to be started. And in the end, an attacker wants to have payloads to do some evil stuff on the PLC. We implemented all 4 parts, and I'm going to show you how we did this step by step. I will start with target discovery. The first thing you need, if you want to find PLCs on your network, is characteristics that allows you to identify them. All Siemens PLCs have an open TCP port 102. So if you find an open TCP port 102 in your network, the probability is high that you found a Siemens PLC. Our basic idea here was to implement a port scanner in the programming language of the PLC. We have 2 system function blocks that helped us. The first is called tcon, it opens a new TCP connection, and tdiscon, it closes a TCP connection. On this slide, we can see the call of the tcon function. There are a lot of parameters that are passed to the function. The most important are the IP address and the port you want to connect to. After the first call of this function, the firmware will process this function in background. And in the next cycle, we come back to this part of the code and call the function again. And now the function will tell us if the connection was established successfully. If yes, we found a new PLC and can continue with our infection. If not, we have a little problem, because this function does not implement a timeout. So we have to do it by ourselves. We simply count the cycles in which we failed to establish a new connection. And if we hit the upper limit, we call the tdiscon function. The function will fail because you cannot close a connection that was never established, but it frees the resources for the next IP address we want to try. In the bottom corner, you can see how we select the IP address as the next IP address. We simply count up the last byte of a 4-byte IP address, and that means we scan and /24 subnet for an open TCP port 102. Okay, that is the target discovery. The next thing is the carrier mechanism. Normally, user programs are transferred with the help of the TIA portal via TCP to the PLC. And our basic idea here was to implement this protocol in the PLC programming language. Again, we have 2 functions, tsend and treceive. You can send and receive any TCP data with them. That helped us with this task. The hard part here was to understand the protocol that is used to download or to transfer programs between the PLC and the TIA portal. The protocol is called S7COM+. It is a binary protocol, and there is no public documentation available on how the protocol is working. There are huge difference compared to the old protocol used with S7 300-400 PLCs. It is slightly modified in the new firmware version or in the S7 1200 devices, and it allows us to transfer programs to the PLC or back into the TIA portal. You can do other things, for example, start or stop the CPU. You can change the outputs with the help of this protocol. Now I'm going to show you what we found out about this protocol. On this slide, you can see the first message that is sent from the TIA portal to the PLC if it wants to establish a new connection. The protocol will start with the magic byte 7.2. After that, there's a version field. There's a length field which tells us how many data is transferred in this message. We have a type field which tells us something about the intention of the message, for example, request, error, response. There's a reserved field. We have a subtype which tells us something about the intention of the message in more detail. And we have a sequence number. The sequence number is simply incremented in every message. In the end, we have a frame end delimiter, and if this frame end delimiter is missing, it simply means that the message is continued in the next message. And between the message head and the frame end delimiter, there are a lot of more bytes. And in the beginning of our analysis, we had problems to find any structure in these bytes. But if you look close enough, you will find a lot of A3 bytes. This A3 bytes introduce a so-called attribute block. Attribute block structures the data that is actually transferred with this protocol. Like the whole message, each attribute block has a basic layout. It starts with the A3 byte. There's an ID field which tells us which value is transferred. In this example, it's some kind of server session. There's a field which is usually 0. It's maybe some kind of format. There's a data type field. In this case, it's a string. A string has a length field, and in the end, the actual value is placed. At the beginning of our analysis, we had problems to pass these attributes correctly because all the the length fields contained wrong values. And this is because numbers have a dynamic size in this protocol. You can see it in the first example, it starts with a 1 bit, and that means there's a following byte, which also belongs to this number. In contrast to that, the 16, it starts with a 0, and that means there's no byte following. After that, we were able to pass the blocks correctly. On this slide, you can see the second message. The second message is replayed by the PLC. It's an anti-reply protection in this message. We are only interested in 1 byte. It's a red framed byte. And what you have to do is that you need to flip the first bit of this byte and put the result in all your messages that you are going to send to the PLC. So you can see the result in the third message here. You need to place the result here, and this is a third message, and the third message completes the connection setup. There's another interesting message that is a program transfer message. The header has 2 more interesting fields. The first is the block type. It defines the program, it defines the type of the program block we want to download, for example, function block, data block, so the ones I mentioned before. And there's a block number. The block number is the place where the program block is stored on the PLC. After that, there are a lot of attribute blocks which transfer a lot of values. For example, the modification time of the program block, the source code of the program block is stored on the PLC. The bytecode that is actually executed by the PLC is stored on the PLC. And some of these values are only used by the PLC, for example, the bytecode, and others are only used by the TIA portal in case you want to receive your program back out of the PLC. Okay, at this point we knew enough to create own messages and to download or transfer own programs, and we started to play with the protocol, and we found some security flaws that are interesting if you want to implement a worm. The first problem is a problem with data redundancy. As I mentioned before, the block number is a place where the block is stored on the PLC, and it's transferred in the message head. But it's also transferred later in the message as attribute block. So the question is, which of these values is evaluated by Siemens? And the answer is both of them. The first is only evaluated or used by the PLC, and the second is only used by the TIA portal. Now, consider the following situation. You create a new program transfer message and choose a free number in the message head, which is used by the PLC. But you choose a number that is already existing on the PLC in the attribute block that is only used by the TIA portal. Now you transfer this message to the PLC, and the PLC will check the message head and will place the program block to a free slot and will start the execution. If later an engineer wants to check the program, maybe he recognizes strange behavior in his industrial network, he will use the TIA portal, and the TIA portal will download all program blocks that are on the PLC. Now, the PLC will get in trouble because it sees that there are two blocks with the same number, but that is not possible. So the TIA portal will solve this problem by only displaying one of the program blocks. And this allows us to hide parts of our code in front of the eyes of the engineer. But this is not working with data blocks. There's another problem with data redundancy. The code is stored twice. It's stored as XML source code. The source code is only displayed by the TIA portal. And the bytecode. The bytecode is executed by the PLC. And if you want to create a missiless program, you just write it, and then you remove the malicious commands from the source code and download everything to the PLC. If an engineer will later check the program that is running on the PLC, he only will see the clean source code and thinks that everything is okay. But the bytecode will execute the malicious commands. And you can leave out blocks that are only used by the TIA portal at all, and this helps us to reduce the size of the worm. Okay, at this point we knew a lot about the protocol. We knew how to set up a new connection. We knew how to overcome the anti-replay protection, and we implemented everything with the help of the TIA portal. The messages that are used to transfer the worm program are stored in data blocks. The problem here is that you cannot create the data blocks with the help of the TIA portal because you only know the exact content of the messages when you finish programming. What you have to do is that you create the blocks manually. You just download the worm with the help of the TIA portal. You capture all messages, receive the messages from the dumps, and create the messages by your own. And then in the end, you can inject everything with your own tool. Okay, that is the carrier. The next thing is the activation function. This is very simple because you need to know that, well, as I mentioned before, organization blocks are the entry point of the program. But you need to know that on PLCs you can have more than one main function. You simply add an additional organization block and the PLC will start the execution of this block. So it's built in and we have to do nothing. In the end, we want to create some payloads, and because we are part of the normal user program, we can do whatever a normal user program can do. For example, we can stop the execution of the PLC, we can manipulate the outputs, we have the TCP functions to implement a command and control server or proxy or whatever we like. Yes, so we implemented all 4 parts, and now I have a little demo. What you will see is that there's an attacker. The attacker will infect the first PLC, and after that the worm will spread over the PLCs, and in the end the worms connect back to our command and control server, which is running on the attacker's computer. So okay, I created a movie. Here you can see our small example factory. The factory is controlled by 4 Siemens PLCs. You can see them in the top corner. And the different parts of the fabric are controlled by different PLCs. In this example, our machine produces little yellow things, and yeah, everything is working normally. What you will see next is that I disconnect 3 PLCs from the network, because I want to prevent the worm from spreading too fast. Okay, I think this will happen now. Okay, now the 3 PLCs are disconnected, and on the right side you can see the attacker screen. The attacker will start a command and control server now. It's a little Python script written by us, and the command and control server waits for new connections. Now the attacker will infect the first PLC. Again, a little Python script written by us, and now you will see that the infection is in progress. It takes some seconds, and now the first PLC is infected. Now I will reconnect the 3 PLCs. Oh, you see the first worm already connected to our command and control server. And now the worm will start to spread over the other PLCs. You can see that the factory is still working normally, but there's a short moment during the infection, and I think it's right now, the yellow piece is not moving, where the original user program is interrupted. So now the second PLC connected, and after this short period of time, the PLC works as usually. Now I think the other 2 are infected, so we have the same problem with this little yellow piece again, and you can see all PLCs are connected now. After that, the factory works normally again. So there's no way to see that they are infected now. What I'm going to show you now is that you can control the PLCs with the help of the command and control servers. For example, we can switch the outputs to values we like. You will see that the slider on the left side will move, but there's no yellow piece. Okay, now it's moving. So you can control the PLCs with the help of the command and control servers. You can start the assembly lines. We can start the next assembly line. Okay, now both of them are moving, and we can stop everything again. We can set the outputs to random values, for example. Now the fabric is out of control, and it is broken now. In this example, it's very easy to repair it. You will see that I have to repair it in a few seconds, so I stopped everything. Now the slider is not moving, but now it's fixed. And in this case, it's very easy. It's a small factory, but if it's a real factory with big and expensive machines, your machines are broken now, maybe. So the next slider is also broken. I fixed it too. Now the factory is working again. What I'm going to show you next is that we implemented a proxy server, and what we can do is that the PLC connects to us, to the command and control server, and we can use this connection to connect back into the industrial network and can reach targets in this network with the help of the proxy server. So the proxy server is started, and now I will do an Nmap scan with, of one PLC with the help of another PLC. Okay, I think the scan will start in a few seconds. Yeah, okay. Now it starts to scan. So the proxy change command in front of the Nmap command just makes Nmap to use the proxy server. You can see that the factory is still working normally. You will not recognize that something strange is happening. I think it will take some time because Nmap will scan, I don't know, 1,000 ports. We will see the result in a few seconds. Everything is still working. And now, where's the result? Oh, there. Okay, we have two open ports, 80 and 443. There's a web server running on the PLC. So now we are able to connect to this web server, for example, and can transfer data, but this is not part of the demo because I think you got the point that we can create TCP connections to all devices that are in the industrial network. The last thing I want to show is the kill function. You can simply shut down the factory by typing in kill, and you will see that in a few seconds. I think right now. Okay, you see the PLCs are blinking, and the yellow please stopped to move, and all PLCs disconnected. That is because the PLC switched into an error mode, and an engineer has to reset the devices device by device to making the factory work again. Okay, that was the demo. Now back to the slides. Okay, we saw that the original user program was interrupted for 10 seconds. And this also generates a log entry in the PLC. But there's an improvement. You can, so we need to stop the original user program because we add a new organization block. And this is only possible if the execution is stopped. But the improvement is that you can patch existing OBs online. You just can add new code to them. This was already shown at Black Hat 2015 in the talk. The talk was called Internet-Facing PLCs. This will work here too, but the worm will get more complex. The worm uses memory, nearly 40 kilobyte of RAM and 220 kilobyte of persistent memory. You can reduce this by, for example, by creating a more specific payload, but it's already small enough to fit in all the different S7-1200 models. The cycle time is important. The cycle time is the time in which you can execute a user program without interruption, and it's usually 150 milliseconds. and our worm, the longest cycle we could measure during the infection process was 7 milliseconds, and that matches our assumptions because we use communication functions the most of the time, and these functions are processed in the background by the firmware. Yes, the worm is part of the normal user program, so the worm will survive a cold restart. If you want to remove the worm, you can do a factory reset, which deletes the complete user program, or you can overwrite the program block that is used by the worm. The TI portal is able to recognize the worm. You can see that on this slide. In the upper corner, we have green program blocks. These blocks are the blocks that an engineer wants to have on the PLC. But in the bottom corner, you see program blocks that are not green, that are new program blocks, and an engineer maybe starts to reserve engineer these blocks now. But what you can do is you can create strange attribute blocks and place them on the PLC, and if the TIA portal download all program blocks, it will crash because of these strange attribute blocks, and an engineer is not able to check the PLC, to check the program that is running on the PLC. This means that the TIA portal is not a good tool to analyze malware on PLCs, on Siemens PLCs. Protection. The S7 provides 3 different protection mechanisms. The first is called know-how protection, and the know-how protection protects unauthorized reading or modification of the code. If you enable this protection, there is an attribute block. You can see it here in the bottom corner that is added to the program transfer message. And there's basically an enable flag, which tells us if the protection is enabled or not. And there is a SHA-1 hash of the password. You have to provide a password when you enable this protection. In addition, the source code is AES encrypted. Now, if you want to disable this protection, what you have to do, you simply download this block with your own tool. Then you change the flag to 0 and upload everything again, and the protection is disabled. The problem here is that the source code is still AES encrypted. And the question is, how is the AES key generated? As I mentioned earlier, this attribute block, you can download it simply by asking the PLC, please give me the program block, and you will get this SHA-1 hash because it's part of the program block. And now how is the AES key generated? It is calculated from this hash. You simply truncate the hash to 128-bit and XOR it with M. The problem is that M is displayed on this slide, and so you are able to calculate the key by your own. So that means that this protection is ineffective because it's broken, and it only protects existing code. But our worm adds only new code. This is fixed by Siemens in the newest TIA portal version. There's another protection called copy protection, and this allows you to bind your program to a specific PLC. You need to enter a serial number of the PLC, and the TIA portal will only transfer your program to that specific PLC. The problem here is that you can simply change the serial number if you have your own down and upload tool, or you just can download whatever serial number to whatever PLC, because this number is only checked by the TIA portal and not by the PLC. So that means it's a client-side protection, so it's not effective. There's a last protection, which is called access protection, and this protection does not protect the program, but it limits the features that are can used without providing a password. So the features of the protocol we use to transfer the program, the worm. And there are basically two different protection levels. The first is called write protection. The second is called read and write protection. And if you enable this protection, you have to provide a password before you can download programs to the PLC. And this is an effective protection until the worm knows the password. It works, but it is disabled by default. So it's a very good idea to activate this protection on your PLCs. Then we looked at other vendors because we were wondering if it's a Siemens-specific problem or if maybe other vendors are infectable too. There are three main features we use to implement the worm. The first is industrial Ethernet. Then we need a way to transfer our program via TCP to the PLC. And in the end, we need programmable TCP functions. And on this slide, you can see a list of leading vendors, for example, Siemens, Mitsubishi, Schneider, or Rockwell Automation. And we checked the PLCs simply for these three features. And there's only one PLC that is not able to, you cannot program it via TCP. And there are some more PLCs that are not able or that not have programmable TCP functions. But you can see there are still a lot of vendors left. So these PLCs might be infectable by worms too. So it's not a Siemens-specific problem. The problem is that you can change user programs without the need to provide a password in the default configuration. So we used no bug or exploit to implement the worm. Everything works as expected. So it's just implementing everything in the PLC programming language. Yes, and that's the end of my talk, and I thank you for your attention.